Thank you, Eric, and good morning to everyone. I am Fabio Caiazzo and I am project manager in the Automotive Fluid Development team. I am working here at the GR&T, focused on e-application and in particular on the assessment of the corrosivity of the novel technology that are implemented in our facilities. The first part of my presentation will be focused on the copper corrosion wire test. As you might remember, last year we presented this test in our webinar. The test was redesigned at PLI, despite its present in literature, with a totally different cell setup and with a dedicated instrument. We moved to a potentiostat in order to better control all the input parameters of the test. On top of this, we decided to introduce the scanning electron microscopy coupled with EDX in order to analyze the surface of the wire after the test, in order to get also information regarding the corrosion mechanism that lead to the failure of the test. The copper wire test was used for the technology assessment of the iona second generation candidate. As we can see, all the technology has improved copper corrosion resistance compared the previous generation, the iona first generation and the standard API GL4 and GL5 technology. However, we need to find a balance between the copper corrosion resistance and the load carrying capacity. These two properties of the fluid need to be fine-tuned on your application. Technology 2 was selected in order to have a high load carrying capacity with medium corrosion performance. From the graph of the copper wire test, we can see that we reach the breaking of the wire after 192 hours. At the same time, we can follow the rate of increase of resistance over time on the secondary axis. These increases for the whole length of the test until we reach the breaking of the wire. It's important to highlight that 192 hours is a good result compared to the previous generation that were reaching barely 20 hours of resistance in this test. Situation gets completely different when we move to technology 4. Technology 4 is able to complete the test, so we reached 336 hours without any issue. Also, the rate of increase of resistance is very low and gets stable over the time. We have a final increase, however, situation is much more stable compared to the technology 2. So in this case, we can say that we have a good corrosion resistance. Moving to technology 6 and technology 7, situation is extremely better from the point of view of corrosion resistance. So we are losing some performance in load carrying capacity, but this is balanced by the excellent copper corrosion protection. In fact, the two plots are completely, the curve in the two plots is completely smooth, and the rate of resistance increase is negligible for technology 6 and in particular for technology 7, which is close to 0 over the time. So the two technology doesn't have any issue to reach the 336 hour end of test. This information, these 4 information, are already enough to accomplish the rating of the technology. However, provides not enough information about the corrosion mechanism. For this, we decide to introduce the scanning electron microscopy and to observe the wire in a microscopic scale. So we move from the optical scale to a microscopic scale, here represented for technology 2. Technology 2 is very interesting, the status of the wire after the test, and is characterized by a thick layer of corrosion product that are deposited on the surface, which reach 105 micron. We have always to remember that we start from a wire that is 64 micron thick, and we have the area of pure copper that remain exposed when the coating made up of corrosion product break that is only 50 micron, roughly 50 micron. This suggests that we have a continuous dissolution of the wire, releasing copper that is used to build up such thick layer. The breaking of the wire might be induced by two phenomena: the decrease of thickness of the wire itself and the increase of the mechanical strength due to the accumulation of the corrosion product on the wire surface. For technology 4, situation is different. The corrosion products that are deposited on the surface are much less thick. We are talking about 500 micrometer thickness layer, which is homogeneously distributed on the wire. For this reason, in this situation, we don't have any mechanical induced stress that might bring to the rupture of the wire. When we move to technology 6 and 7, which were showing excellent corrosion protection, situation is completely different. In both technology 6 and technology 7, we have a surface that is very clean without any precipitation of corrosion product, at least at a macroscopic level. The difference between technology 6 and 7 is that in technology 6 we have a localized attack on the surface visible in several points of the wire. For technology 7, situation is different. We have an homogeneous dissolution of the wire that brings the wire to a final thickness of 63 micron. So a very smooth homogeneous corrosion phenomena. Additional information were provided thanks to ADX analysis. The ADX analysis allows us to access to the chemical composition of the surface of the wire. For technology 2, for example, we clearly see the presence of area of sulfur and copper, which are perfectly overlapped on the corrosion product rich area. While in the area where the wire is exposed, we only have the signal of the copper. Much more homogeneous and uniform is the surface for technology 4, 6 and 7. For these three technologies, we have a uniform distribution on the surface of sulfur, which clearly is due to corrosion product for technology 4, which are visible at macroscopic level together with copper, they form copper sulfide. While for technology 6 and 7, sulfur, which is deposited on the surface, is due to the sulfur free which is present in the fluid and might interact with the surface of the wire. We need to consider that to achieve such excellent corrosion resistance performance, we need to have a chemistry with low sulfur content. So ACM was crucial for the failure analysis and for understanding what is happening on the surface of the wire during the corrosion process. However, ACM is an extremely powerful technique that PLI decided to implement in its lab and offer to customers to run troubleshooting activities for their development. Now I will guide you through a real case of troubleshooting performed on e-motor, in particular on e-transmission of first generation, where the reduction gear is separated by the e-motor through a seals. The seals is also the weakest link between the e-motor and the reduction gear, because in case of damage of the underlip, we have the contact among the fluid and the motor itself. If fluid goes in contact with the motor, then we will have to assess the compatibility between fluid and the component. In particular, this activity is focused on the rotor, which is contained in the e-motor. We decide, together with the customer, to divide the activity in two sub-activities: the determination of the failure analysis of the tested part and the identification of the root cause analysis, which determine the failure of the part. Failure analysis was performed by means a non-destructive technique inspection of the part. In this section, we'll see the results of the failure analysis we carry out on the rotor part we receive from our customer. The first one that we can see is an optical image of the surface of the rotor that has been taken by a microscopy. Going more in detail, we can see the presence of some tarnished area that can be reminded of some corrosion attack, and presence of dry droplets that also in this case suggest the contact between the part and the fluid. The second part of the activity was focused on the identification of the causes that lead to this type of degradation. Together with the customer, we work to identify the best testing condition. So we work on the definition of the environmental condition, in particular the thermal cycle, which were carried out for several months, so itself the number of cycles, and the exposition condition, because it's important to assess how the fluid can be in contact with the parts. We identify three conditions: configuration A, B, and C. In configuration A, the parts are exposed only to the corrosivity of oil. In particular, we expose the part to vapor, fluid, and the interface between fluid and vapor. Then moving to configuration C, this configuration was defined to have a control condition in order to assess the effect of the humidity present in the environment. Then configuration B combines the two effects. Cells are open, can communicate with the external humidity of the environment, but also as the presence of oil, so the corrosivity of oil itself. For such type of test, which is carried out for several months, is crucial to document the status of the surface in the pristine state. To do this, we carry out optical inspection of the part and inspection of the part by means scanning electron microscopy and also EDX mapping. The EDX mapping allows us to assess that the condition of the surface, and in particular we see that the surface is clean. We have only presence of iron signal and some oxygen due to some point of rust that are already present in the pristine state. The test is still ongoing, but today we are able to show you the results regarding configuration A and C. Let's start from configuration C, so where we assess the corrosivity due to only the humidity which is in the environment of the test. The surface looks like damage with a reddish color. This color is clearly associated to a layer of iron oxide which is formed on the surface due to the condensation of the water that takes place on the surface of the part. This is also confirmed by the ACM image that shows a contrast in the backscattered image, and also in the EDX analysis we observe the presence on the surface of iron and oxygen. Moving now to configuration A, the result is very different according to the type of exposure we have. We have a dark surface which characterizes the part which is exposed to the vapor, while the part exposed to the liquid phase is still clean with a bright look. Moving now to the part exposed to the interface, we can see that there are two different conditions of the surface. A more damaged part, which is the part exposed to the vapor, and the bright part, which is exposed to the liquid. More interesting is when we move to microscopic dimension and we have the ACM image. The ACM image of the part which is exposed to the liquid is very bright and suggests that the surface is still covered mainly of iron, is mainly constituted by iron, and we only find some residual of oil present in some small region. We can see from the EDX image that in fact the color of iron is present widely on the surface. Vice versa, for the exposition to the vapor and the exposition to the interface liquid and vapor surface is covered by a thick layer of deposit of fluid that get vaporized on the surface. However, it is important to highlight that in all these conditions we are not able to find issue of corrosion. We don't have corrosion attack, so we can say that the exposure to pure oil is not leading to the damage of the part through a corrosion process. We are now at the end of my speech, and I would like to leave you with the outcome and the take-home message of my presentation. The copper wire test is a key test for the assessment of the corrosion behavior, but as well the corrosion mechanism of lubricant. PLI support is not limited to fluid development, but it also includes a broad experience in troubleshooting and setup of customized tests to promote the development of your final system. So, thank you for your attention and see you at the Q&A section.